Hi, good morning, everyone. This is Adalim Bermel, one of the reporters on the topic implicit functions and extremum problems. Let's start from the introduction. This chapter consists of two principal parts. The first part discusses an important theorem of analysis called the implicit function theorem. The second part treats external problems. Both parts use the theorems developed in Chapter 12. The implicit function theorem in its simplest form deals with an equation of the form if xt equals 0. The problem is to decide whether this equation determines x as a function of t. If so, we have x equals g quantity t. For some function g, we say that g is defined implicitly by 1. The problem assumes a more general form when we have a system of several equations involving several variables, and we ask whether we can solve these equations for some of the variables in terms of the remaining variables. This is the same type of problem as above, except the x and t are replaced by vectors, and f and g are replaced by vector-valued functions. Under rather general conditions, a solution always exists. The implicit function theorem gives a description of these conditions and some conclusions about the solution. An important special case is the familiar problem in algebra of solving in linear equations of the form summation n g equals 1 aij xg equals I equals 1 to infinite n 2, where the aij and ti are considered as given numbers and x sub 1 to infinite x sub n represent unknowns. In linear algebra, it is shown that such a system has a unique solution if and only if the determinant of the coefficient matrix A is equal to aij is non-zero. Note that the determinant of a square matrix A equals aij is denoted by det A or det aij. If det aij is not equal to 0, the solution of 2 can be obtained by Cramer's rule, which expresses each x sub k as coefficient of two determinants, say x sub k equals a sub k divide d, where d is equal to det a sub ij and a sub k is the determinant of the matrix obtained by replacing the kth column of A sub aj by t sub 1 to t infinite. For a proof of Cramer's rule, see reference 13.1, theorem 3.14. In particular, if each t sub I is equal to 0, then each x sub k is equal to 0. Next, we show that the system 2 can be written in the form 1. Each, ex- each equation in 2 has the form x sub I quantity xt is equal to 0, where x is equals quantity x sub 1 to infinite x, and t is equal to quantity t sub 1 to t infinite. And we have the formula below. Yeah, you can read that one if you want to read, but for me, it's hard for me to read. Okay, let's proceed to the next um, slide. Therefore, the system N2 can be expressed as one vector equation f xt is equal to 0, where f is equal to f sub 1 to f infinite. If d sub j, f sub I denotes the partial derivative of f sub I with respect to the gth coordinate x sub j, then d sub j f sub I quantity xt is equal to a sub I j sub aj. Thus, the coefficient matrix A is equal to A sub Aij, and 2 is Jacobian matrix. Linear algebra tells that 2 has a unique solution if the determinant of this Jacobian matrix is non-zero. In the general implicit function theorem, the non-vanishing of the determinant of Jacobian matrix also plays a role. This comes about by approximating f by a linear function. The equation f xt is equal 0 gets replaced by a system of linear equations whose coefficient matrix is the Jacobian matrix of f. Notation: if f is equal to f sub 1 to infinite to f infinite, the x is equal to x sub 1 to x infinite. The Jacobian matrix df quantity x is equal to d sub j f sub I. X is an n cross n matrix. Its determinant is called a Jacobian determinant and is denoted by G sub t quantity x. Thus, okay, as you can see on the screen, we can see the formula here. This is our formula for that one. So now let's proceed to the next slide. The next theorem relates the Jacobian determinant of a complex valued function with its derivative. Theorem 13.1. If f is equal to u plus iv is a complex valued function with a derivative at a point z and c, then j sub f quantity z is equal to absolute value of f complement quantity z absolute value squared. Proof: we have f complement z is equal to d sub 1 u plus I d sub 1 v. So absolute value of complement z squared is equal to d sub 1 u squared plus d sub 1 v squared. Also, j sub f z quantity z is equal to that. Yeah, so yeah, this is the solution for that one by the Cauchy-Riemann equations. Omegs, next slides. Okay, now let's proceed to 13.2, function with non-zero Jacobian determinant. This section gives some properties of functions with non-zero Jacobian determinant at certain points. This result will be used later in the proof of the implicit function theorem. As what we can see here, we have figures. Yeah, so that's the example of non-zero Jacobian determinant. Let B is equal to B quantity A R be an n ball in relation to n. Let is that an alpha or beta or variance? I'm not sure about that variable. Okay, let's say that is okay. B denote is boundary. Its boundary. Yeah, so if you want to know more about the explanation of that one, please read the details on, please read the details below the figure. So let's proceed to the next slide. Then gx greater than 0 for each x in B because if x is not equal to fa if x element B, also is continuous on B since f is continuous on B, since B is a compact, J takes on its absolute minimum, call it M, somewhere on B. Note that M greater than 0, since G is a positive on B, let T denote the n ball. So we have here our formula for that one. T is equal B times F quantity A M over 2. We will prove that what is this one? Com okay, we'll prove that T. Alright, so please, I'm so sorry about this one because I forgot how to read this math symbols. And this will prove the theorem. So please see the figure on 13.1. To this we show that y element T implies y element if B. Choose a point y in T. Keep y fixed and define a new real valued function h on B as follows. So we have that one. So next, please, let's proceed to the next. Then h is continuous on the compact set B and hence attains its absolute minimum on B. We will show that h attains its minimum somewhere in the open end ball B. At the center we have HA equals, is that absolute sign? I'm not sure about this one. If A minus Y less than M divide 2, since Y element T. Hence the minimum value of H in B must also be less than M divide 2. But each point X on the boundary B we have. Okay, that's the solution for that one. So the minimum of each cannot occur on the boundary B. Hence, there is an interior point C and B at which H attains its minimum. At this point, the square of H also has a minimum. Since H squared x is equal to absolute value f x minus y squared equals summation power n r equals 1 f sub r x minus y sub r squared, and since each partial derivative d sub k quantity x squared must be 0 at c, we must have this one. Please try to look at this one. I'm not going to read that one because I don't know how exactly I don't know how exactly to read this. It's so difficult. But this is a system of linear equations whose determinant g sub t c is not zero since c element b. Therefore, f sub r c equals y sub r for each r, or if c equals y, that is y element if b, hence t. Okay, here we are again. I don't know how to read that one. And proof is complete. A function f s, a function if s then t from one metric space s d sub s to another t d sub r is called an open mapping f. For every open set A in S, the image if a function A is open in T. The next the next theorem gives Theorem 13.3. Let A be an open subset of relation N and assume that A F if A, then the relation N is continuous and has finite partial derivatives. They sub j f sub I on A. If f is 1 to 1 on A, if g sub t x is not equal to 0 for each x in A, then function A is open. We have our proof here. Okay, so that this is the solution or the proof of that theorem. So let's proceed to theorem 13.4. Assume that f equals f sub 1 to n to f infinite has continuous partial derivatives. They sub j f sub I on an open set S in a relation N, and that the Jacobian determinant j sub f a is not equal to 0 for some point A in S. Then there is an in-ball BA on which F is 1 to 1. Okay, and we have here the proof to theorem 13.4. You can read that one if you want to know more about the theorem 13.4. So now let's proceed to the next slide. This function is continuous at those points j, z, and relation n squared, where each j, z is defined because each d sub j, f sub I is continuous on S, and a determinant is a polynomial in its n squared entries. Let Z be the special point in R, a relation n squared obtained by putting z, z sub 1 is equals to z sub 2 is equals to ellipsis infinite equals A. Okay, now let's proceed to the next slide. Okay, theorem 13.5. Assume the contrary, that is, assume that function x is equals to function y. For some pair of points, x is not equal y, and BA, since BE is convex, the line segment L, xy, I don't know what that is, BA, and we can apply the mean value theorem to each component of f to right. So that's the solution of that one we can see on our slide. Okay, next. The determinant of this system is not zero since okay, so this is the whole details of the theorem 13.5 if I'm not mistaken. So if you want to know more about that theorem, please try to read this one. So now let's proceed to the next slide. Okay, so the next is theorem 13.5. Let A be an open subset. I think this is the continuation of the theorem 13.5. So, yeah, if you want to know more about the 13.5, then please try to read this one. So, let's proceed to the next theorem. Okay, so the next topic is the inverse function theorem. This is the theorem 13.6. Okay, wait for a moment. Mm. Assume f is equal to f sub 1 to f infinite element C complement on an open set S and relation N, and let T is equal to f function S if the Jacobian determinant J sub R, G sub S, G sub F A is not equal to 0 for some point A in S, then there are two open sets X, S, and Y, T, and uniquely is the union uniquely determined function G such that okay we have here A, B, C, D, and A, E. What makes next? Okay, so this is the proof for for the previous slide. So if you want to know more about it, so just try to read and understand this slide. So now let's proceed to the next one. Okay, so I think this is
Okay, so the continuation of the report. Okay, so the set B, the closure of B is impact and if is one to one and continuous on B. Hence, by theorem 4.29, there exists a function G, the inverse function of f to the power of negative 1 of the theorem 4.29 defined on f b such that g f of x is equal to x for all x in b. I don't know if how to read that one, that b with the sign above. I'm not really sure about that. Okay, so moreover, g is continuous on f of b. Since X is a subset or equal to B and Y is a subset or equal to FB, this proves parts A, B, C, and D. The uniqueness of G follows from D. Okay, so next we prove E. For this purpose, define a real valued function h by the equation h of z is equal to that d sub uh, dj fi zi, where z sub 1 z and are n points in S, and z is equals to z sub 1 infinite zn is the corresponding point in r to the power of n squared. Then, arguing as in the proof of theorem 13.4, there is an n ball or b sub 2 a such that h is to z is not equal to 0. If each z I is belongs to b sub 2 a, we can now assume that in the earlier part of the proof, then n ball b is to a was chosen so that b a is a subset or equal to b sub 2a. Then b is a subset or equal to b sub 2a, and h is to z is not equals to 0 if each z I is belongs to B. Okay, to prove E, write G is equals to G sub 1 dot Gn. We will show that each G key is an element or belongs to C, how to read that next? C1. Okay, on Y. Okay, so to prove that G key exists in Y, assume that Y belongs to Y and consider the difference quotient. So G key Y plus TU sub R minus G key Y over T, where U is the R unit coordinate vector since y is next. Please next, Omegs. Open y plus tu is belongs to y. If t is sufficiently small, let x is equals to g y and let x is equals to g y plus tu sub r. Then both x and x to the power of 1 are in x, and f(x) is equals to f of x equals tu. Hence, f I x minus f sub I in x is 0 if I is not equal to r, and is t if I is equals to r. Okay, by the mean value theorem, we have this one. Okay, so everyone try to look at this one and read it for yourself. Okay, so because I am not really sure on how to read this one. Okay, where each zi is on the line segment joining x and x, how I don't know how to exactly read this, and hence z sub I is belongs to B. The expression on the left is 1 or 0. According to whether I is equals to R or I is not equals to R. This is a system of n linear equation is n unknowns. So xg is equals to xg over t or divide t and has a unique solution since, okay, so that dgfi is to z and I is equals to h to z is not equals to 0. Solving for the kth unknown by Kramer's rule, we obtain an expression for j key y plus tu sub r minus g key y um divide or over t as the quotient of determinants. As t is to 0, the point x is to x. Since g is continuous and hence each zi to x, since z sub I is on the segment joining x to the power of 1. The determinant which appears in the denominator has for its limit the number that dg fi of x is equals to g sub f of x, and this is non-zero since x is belongs to x, therefore the following limit exists. Okay, so these are um the solution or the formula on how to solve that one. Okay, please next, Max. This establishes the existence of d sub r g sub k of y for each y and y and each r is equals to 1 2 dot n. Moreover, this limit is a quotient of two determinants involving the derivatives djfi of x. Continuity of the djfi implies continuity of each partial d sub r g sub k. This completes the proof of E. Okay, so note the foregoing proof also provides a method for computing d sub r g sub k of y. In practice, the derivatives d sub r g sub k can be obtained more easily without recourse to a limiting process by using the fact that if y is equals to f of x, the product of two Jacobian matrices df of x and dg of y is the identity matrix. When this is written out in detail, it gives the following system of n squared equation. Okay, so like this one. The summation of n k is equals to 1 d k g I of y dg f sub x of x is equals to this one. Okay, so I don't know how to exactly read this one because I am not really good on reading the mathematical symbol. Okay, so for each fixed I, we obtain n linear equations as the g runs through the values 1, 2, dot, 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 n. Okay, so this can be solved for the n unknowns d. Okay, so let's go on to the 13.4. The implicit function theorem. The reader knows that the following equation of a curve in a xy plane can be expressed either an explicit form such as y is equals to f of x or in an implicit form such as f of x and y is equals to 0. However, if we are given an equation of the form f of x and y is equals to 0, this does not necessarily represent a function. Okay, take for example, x squared plus y squared minus 5 is equals to 0. The equation f of x and y is equals to 0 does always represent a relation, namely that set of all. Okay, please next, Max. Pairs x and y which satisfies the equation. The following questions therefore presents itself quite naturally. Okay, when is the relation defined by f of x and y is equals to 0 also a function? In other words, when can the equation f of x and y is equals to 0 be solved explicitly for y in terms of x, yielding a unique solution? The implicit function theorem deals with this question locally. It tells us that give a point x sub 0 and y sub 0 such that f of x sub 0 and y sub 0 is equals to 0. Under certain condition, there will be the neighborhood of x sub 0 and y sub 0, such that in this neighborhood, the relation defined by f of x and y is equals to 0 is also a function. These conditions are that f and d sub 2f be continuous in some neighborhood of x sub 0 and y sub 0, and that d sub 2f is x sub 0 and y sub 0 is not equal to 0. In its a more general form, the theorem treats instead of one equation in two variables, a system of n equations in n plus k variables. Okay, so these are the formula or the example of that one. Like f sub r is x sub 1 dot 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 xn t1 dot 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 to t sub k is equals to 0, and